Hello, thank you very much for the introduction. It's a pleasure to be here, if I may say. I mean, it's 11 p.m. here in Japan, and I'm actually very happy also that was possible to make accommodations to accommodate my my schedule, because I will maybe fall asleep in 1 or 2 hours or so. So today I'm going to speak about on a joint work, about the joint work with Charles Bordenave, who is at CNRS in Marseille. And actually, well, we have done 2 joint papers, and I'm mainly going to speak about the second one, which is a preprint which we released on Archive earlier this year. So I will state our results, which is about the norm convergence of multi-matrix models which actually involve tensors. So I was a little bit I left it a little bit fuzzy in my title, but I decided to speak about the tensor version of our results. And so the main result itself, well, I suppose, is of some interest, but techniques needed to prove this result, I think, also have their own interest. So there is this operator value non-backtracking, which we developed together in our first paper, which we developed further in this second paper, which is somehow some pure operator algebra or functional analysis techniques. And then there are some techniques which are more like probability or random matrix specific, which I'm going to explain, to talk about as well, because they are needed for the proof. So yeah, one more comment before I move on. I was actually hoping to annotate my slides while talking to make it more lively, and actually my slides were prepared with that in mind. So that's not going to be possible because of seemingly some recent update on Zoom. So yeah, I'll try my best to catch up orally by hand waving and mouse waving maybe. So a few reminders. First, about non-commutative distribution and convergences. So here, basically copying the setup of Voiculescu for non-commutative probability theory. So we have a sequence of non-commutative probability spaces, which I call, this is pairs indexed by n, and this is an tau n, where so A is a unital star algebra, where for me it will mostly be a fundamental algebra, but that could be something else. And tau is a tracer state. And so n, typically it will be a dimension. I will be mostly looking at matrix algebras, but actually n might not be the dimension. I mean, the dimension would be a function of n, and this will be a dimension of a representation of a group or something like this, of the unitary group UN or something, which is what I will be focusing on actually. So then we take a d-tuple of elements there. So elements of non-commutative probability tracer state are called non-commutative random variables. So I take a d-tuple of random variables, and I would like to define what it means to converge in distribution to an object of the same type at the limit. And well, it just means that for any non-commutative polynomial in the variables and its adjoint, if I evaluate, so if I take the what did I do? I made a mistake. Okay, made a mistake. Let me try to. Sorry. So what's going on? I don't know what happened. Sorry. Oh, yeah. No, that's right. Though. Yeah. Okay. Whatever. I changed the app, but okay. Whatever. Okay. So right. So the convergence in the non-competitive distribution means that whenever I have a non-competitive polynomial p in variables, which when I apply it to in the d tuple of variables, then it becomes an element here. And if I apply its trace, then it should converge to the trace of p for the limit. And well, I said I'm going to take a fundamental algebra. So I have an operator norm. Actually, well, a C-star algebra would be good enough. And if in addition, for any polynomial, I have a convergence of the norm, then one speaks of strong convergence. So here, one remark is that the limit object is going to involve free products, but like it's going to be something like a free group algebra, something like this, in general. But the ANs are in general going to be matrix algebras or random matrix algebras. So maybe like some matrix tens, some classical probability space. And so one thing is, which one could wonder is, what is the relation between this and that? And the relation is that when the traces are faithful, which is what we're always going to assume, there is something which we can say at least about the limit inf of T of a non-commutative polynomial applied in my d tuple of variables. Namely, the limit inf is always at least p of the norm of p of xi here under the assumption of convergence. So here we have convergence, which was introduced by Voiculescu, and here we have strong convergence, which has been around for a long amount of for maybe 15 years now, because the first real results in this direction are from Hargrove Thomas. I'm going to get back to it, but probably it's Camille Mal and me in a joint paper who introduced this terminology. So we have this inequality, and something which is important is that this inequality can be strict. So, for example, if we take, you see, so here the example which I have in mind is if you take some Lyubodsky-Phillips Sarnak generators of a Ramanujan graph, for example. So here you have unitaries. Okay, you have a d tuple of unitaries, and if I take the sum, if I take the norm, the sum of ui's, in principle, the norm should be like something like 2 root d minus 1, something like this. But if I take this quantity here, it will automatically be d. And for d large enough, of course, this is bigger than 2 roots d minus 1. So in this case, we have strong convergence. We have convergence in this sense here, but we don't have convergence in that sense. So from the point of view of random matrix theory, somehow strong convergence addresses the question of, do we have eigenvalues which are misbehaving? Like, do we have a small number of eigenvalues which are away from the limiting spectrum? That's really the question which one wants to address. Okay, so so far, in principle, even though my example already involved freeness, so far, in principle, all what I'm saying is about convergence and strong convergence, and it does not necessarily involve freeness. Actually, there are some very interesting recent developments where we have some convergence results which go far beyond freeness, like some very interesting results from Michael Maggie, for example, recently. But I will just stick to freeness, and actually most of the non-trivial existing results so far in the multi-matrix setup is related with freeness. So if the limiting distribution is free, so if the limiting objects are star free, U1, UD, here somehow I renamed my X1, XD into U1, UD because I'm going to speak about freeness. Then we speak about freeness, and if the norm convergence, which is here, holds as well, then we have strong freeness. So a little bit of history. So historically, I think the first examples of freeness, well, I mean, maybe the most famous example of freeness was given by Voiculescu in 1992, 91, 1993, where he proved that if I take here x1, xn to be GUE, so you just take self-adjoint Gaussian matrices, independent at random, then they converge. And so here this is n by n matrices, n by n random matrices, but you just take a sample and you just see what happens with high probability. And then what you see is that they will be asymptotically free with high probability, with probability 1, actually. This is what Voiculescu proved, and well, then he did the same later, a little bit later in a subsequent paper with not Gaussian matrices, but matrices which are distributed according to the Haar measure on the unitary group. So Haar matrices, and he put this converges to what he calls a free Haar unitaries. Actually, I think that Nika did a little bit earlier the case of random permutations. If I just take permutations which I see as matrices with entries, like as unitary matrices with entries 0, 1, and if I pick them at random according to the uniform measure on the symmetry group, then Nika showed also that if that I have asymptotic freeness. And well, basically what it boils down to is if you take a non-trivial product of permutations, and in their inverses a non-trivial word, then the number of fixed points is a little O of n, so goes to 0 relative to the size of the number of points which are being permitted aesthetically, which is what the normalized trace accounts for in this case. So yeah, maybe I'm also going to mention briefly Bian's example with Uchis-Murphy elements, because first of all, this has to do with representation theory, which I'm going to mention, which is going to be my object of study later. And also, what we have here somehow is basically Voiculescu first proved that if we have tons of randomness, like Gaussian is like as random as it can get somehow, or Haar distributed is also like extremely random within the context of a group. Then we have freeness, which is maybe expected somehow. I mean, like the most random thing gives free somehow, and then somehow what we could say from a point of view of probability theory is that even if we have less randomness, like Nika says, well, let's just take random permutations, which are much less random in the sense than Haar unitaries, then we still have asymptotic freeness. And Bian says, well, even if we have no randomness, we can still achieve asymptotic freeness. in some cases. So all these examples here are actually examples of classical convergence, but they are not example of strong convergence. And the point is, well, what can we do with norm in the case of strong convergence? So the big breakthrough comes from Hagerup Torbenson in 2005, where they, in their famous, like almost 100 pages analysis paper, they proved, they revisited Vauquelin-School's results, and they proved that not only asymptotic freeness holds in this context, but also the norm converges. So, which was really a big, very big fit. Once they set up the right techniques, about which I'm going to speak a little bit later, it was extended in many directions by many people. So I'm just here going to mention results by Mireille Capitaine, Catherine Donati, Camille Mal, but many other people made extension in many directions. Always in the context of self-adjoint random matrices. And the case of arbitraries was actually settled by Camille Mal and myself by using a trick, a small additional trick on top of Hagerup Torbensen's result, actually we have a very non-explicit convergence. And here I would just like to remark that actually Félix Parot, the former PhD of me and Alice Guyonnet, obtained very explicit bounds by completely new methods, which are also quite interesting. So, I'm not going to speak about it today, even though I hesitated. Right, and finally, so going into like examples so far somehow. Before going to the main theorem, Charles Bordenave and I obtained also strong convergence results. Somehow what we did is, we revisited Nika's examples. And in the examples of Nika, we know that strong convergence does not hold because we have a Perron-Frobenius eigenvalue, which makes it impossible for strong freeness to hold. But what we show is that as soon as we get rid of this Perron-Frobenius eigenvalue, then strong convergence holds with high probability as n goes to infinity. And so somehow we were interested in seeing whether the techniques which we developed here, which I'm going to explain a little bit later, whether we could extend these techniques to the context of tensors, of random tensors. So here is our main result. So what we're doing is we fix two numbers, q plus and q minus, two integers, and we are looking at the following matrix model. So I take U1, UD, who are IID independent, identically distributed, hard distributed random matrices of dimension n. And then if U is such a matrix, of course, U bar, which is the entry-wise conjugate. So if you want, is the representation, is the morphism associated to the contra-gradient representation. If I take tensor of these guys, Q minus times, and Q and UI Q plus times, then this is strongly asymptotically free as, I see something in the chat. So let me try to see if repeat. So actually, maybe I didn't express myself well enough. So I just mentioned. So I just mentioned two words. So answering the question of the chat, there was one result of Charles Bordenave and me about random permutations, which was published in Annals last year, and one result of Camille and I, which was published in Annales de l'ENS long ago. And then there is this result by Felix, which is under review. So what we have, getting back to this random matrix model. So you see now what we have is this is a random matrix. So it's unitaries, tens unitaries, tens unitaries. So it's a unitary matrix, but of large size, not of size of not in Mn anymore, but in Mn tensor Q plus Q minus. So it's a Q plus Q minus fold tensor product of matrices of n by n matrix algebras. And well, for example, actually, if Q minus and Q plus are the same, then we have fixed points. So the fixed points, of course, will make it possible to have strong asymptotic freeness. Like we will have some deterministic random eigenvalues which are not compatible with the asymptotic freeness estimates. So what we have to do is we have to look at the orthogonal of the fixed point space, and then what we have is in this case a strong asymptotic freeness holds. Then we have a corollary which maybe is nice from a point of view of rotation theory, which is if we take this Russian school notation of signature for irreducible rotation of the unitary group or of GLN of C. You see, when we take the highest weight, we take the positive part and the negative part of the highest weight, and we rearrange them both in Young tableaus. And this gives a natural sequence of representations of the unitary group. So if you want, it's a sequence of subgroups of UN to the power Q, which are some quotients of UN themselves. And then if we take the Haar measure according to it, then we again have strong asymptotic freeness with respect to this. So again, comparing with the results of Nika and so on, somehow what we are achieving here again is to have less randomness in a sense from a probabilistic point of view, because now we have just the randomness somehow of n dimensional of the UN group in a very large dimensional, embedded in Mn tens Q minus plus Q times. So we can also say that somehow this corollary which I have here is some kind of 0-1 law. Basically, it tells that the only obstruction to strong, I mean, in this context somehow, it tells that the only obstruction to strong freeness are the fixed points. The fixed points are obviously not giving, cannot give freeness because this is a dimensional one rotation. But as soon as we get rid of this, then we have strong freeness, which in this sense is a really vast generalization of strong asymptotic freeness, which Camille and I obtain. Well, the comment below that the corollary and the main theorem are equivalent is just some simple Chauvel duality, so I'm not going to spend time on that. And before moving to the proof, like to the tools. I'm not going to give the proof, but to give an outline of the ingredients needed for the proof. I would just make some geometric, or maybe I could call them philosophical considerations. I mean, geometry is not philosophy, of course, but which is that if you think about asymptotic freeness, which involves hard unitaries, then you take a word and the trace tends either to 0 or to 1. So if it tends to 1, if and only if we have a trivial word, and else in other cases it tends to 0. And what am I doing here? I'm taking tensor products. Okay, I'm taking tensor products. So what does the trace do? The trace is just a product of traces. It's just a product of normalized traces. So somehow, if something tends to either 0 or 1, then its power Q tends also to 0 or 1. So in a sense, this result is not surprising. And actually, if you want to prove asymptotic freeness just in the sense of Voigt-Colescu, then you can do it in the field lines. I mean, by the way, we did something also much more general in this direction with Pierre-Yves Gaudreau-Lamar and Camille Mal. But if you just look at asymptotic freeness in Voigt-Colescu's sense without this strongness, without these norm conceptions, this is not surprising. On the other hand, and this is why it's a bit strange somehow, the evaluation of the operator norm here is much harder because the operator norm is a soup, right? And when we work on the n by n matrices, and here I wish I could annotate, but I can't. When we work on the n by n matrices, we just have to take a soup on an n-dimensional sphere. Maybe if we look really in the complex setup, it's maybe a 2n minus 1 dimensional sphere or whatever. But it grows as n. And now what we have to do is we have to do the same, but something which grows as n to the power cube. And just to give maybe an idea why the result is not trivial and quite counterintuitive. If instead of proving strong asymptotic freeness, which is involved, we just wanted to obtain some soft bounds. You see, like some bounds, somehow in the flavor of a high group inequality or something like this, maybe up to some universal constant or whatever, and independently on the number of generators. Then actually, if we're doing things with the classical Haar measure, then it would be easy to do it with just a net argument and a concentration of measure argument. And here the thing is, you see, if I have Mn, if I'm just looking on the unitary group Un on Mn, then an epsilon net, eta net grows as exponential n, and the concentration speed is also exponential n. So somehow you can strike a good balance, make a deal between these two things, and if you're happy to get strong asymptotic freeness with let's say with a coefficient 6 or 100, whatever, then you can do it actually. But in our general case, it's strictly impossible because now the eta net, we're not doing it anymore on n, on something of dimension n, but on something which is n to the power q, where here I wanted to annotate it. Q is q minus plus q plus. So q is strictly bigger than 1 anyway. So it's impossible. You could do whatever you want with eta epsilon. This is just a dead end. It's not going to work. So in a sense, even though convergence, classical, non-strong convergence should really work, strong convergence is much less nature from our point of view. So how does the proof work? Well, here again, one more word of history. I think it's fair to say that Voiculescu's initial results sometimes they relied on some analysis, but it was always possible to remove the analysis with a little bit of work, and basically most of the initial asymptotic freeness results could really be done with combinatorics. And on the other hand, all the strong convergence results, everything which followed basically the breakthrough of Hardorp and Torbenson, they were relying, on the contrary, on like a tough analysis, and like there was some a matrix valued still just transforms, then integration by branch, finger Dyson, or loop equation, or lots of techniques which and here if you look at finger Dyson or loop equation, which really rely on the smoothness of the underlying properties. So some smart complex analysis techniques as well. In other words, the moment methods were too bulky to implement, and actually the only, I might be mistaken, but as far as I can tell, the only place where moment methods were really of some concrete use to obtain some norm convergence of random matrices were for single matrix, for not for multi-matrix, but for single matrix models, with the very important results of Sinai Soshnikov and many followers. Like a series of results which were implemented 20 years ago, started like 25 years ago or so. But yeah, the point is that if you really wanted to do moment techniques to get norm estimates for multi-matrix models, it was not really possible until Charles and I developed new techniques to actually work with to prove norm convergence results with moment techniques. So the reason why it was, when I say too bulky here, it's what so the thing is, if you want to do to prove norm convergence in a random matrix setup with moments, what you have to do is you have to be able to compute high moments of a matrix, and the degree of the moment has to grow at the same simultaneously with dimension. So it has to grow at least at a logarithmic pace in comparison to the dimension of the matrix. But of course, it's logarithmic. So if I have one matrix, then this is somehow it can be high. But as soon as we have a multi-matrix, since they don't commute, then we end up with like an exponential growth, which you cut at a logarithmic height, and this is a big mess actually. So a direct moment method remains as of today too bulky to implement, and so we have been able to do some moment techniques, but we had to modify the moment approach. And so what I want to do now is to say one or two words about that. So this is not today's main result, but this is like some preliminary things which we did 2-3 years ago with Charles. So there is this step which actually is not ours. It's really, this is the linearization trick. So if we want to evaluate norms of polymers, all this boils down to understanding the spectrum of a linear version, but and the price that you have to accept to pay is to look at matrix coefficients. So in the case of unitary, it's even slightly simpler. So, and actually it had been known by PZ, or like even way earlier than Hagerup, Torvalds. You can just work with the norm actually in this case, and so we have to compute this. So it looks already that studying this might be simpler than studying these kinds of quantities which are here, right? If I want to make moment techniques, but that's not enough actually. If I try to evaluate the norm of this remains too hard. So what we have to do is we have to start from this and do one more step, which is to introduce the operator valued non-backtracking matrix, or actually even in our case operator. So in our first paper we just did it with permutations, and here I'm going to explain it for general unit arrays. So what we do is actually for arbitrary elements in a Hilbert space, the non-backtracking operator associated to the L tuple of matrices here. So actually, yeah, you might wonder what is the ratio between L and D. What will happen? What happens in the proof is that L is actually a 2D plus 1. Somehow what we do is we have our unitary matrices, and we have the identity, all the unitary matrices, and all their inverses. So this is like L is 2D plus 1. And then we create this operator, this funny operator, which is not anymore an operator in B of H, but an operator in the L by L matrices on B of H. So here we have this involution, you see, which could be anything, but which in our case accounts for going between U and U inverse. And what we do is so these are the canonical matrix elements in the L by L matrices, and we just sum over all J's which are not the involution here. So we start from this L tuple, we create this matrix, and the point is that this matrix here, so you can forget about it. That's just something which you should have erased. The point is that the spectrum of this matrix is actually is closely related to the spectrum of a matrix which can be constructed out of the B1 BLs. And then what we do is we realize a matrix like this as something like this, and then by some kind of inversion thing, we obtain a B, and it turns out that we are able to say something about the spectrum of B with moment techniques, which in turn allows us to say something about something like this, which corresponds to that, and in turn to say something about the norm of this operator. So that's the operator algebra, which is under the hood somehow. Then what we have to do is we have to do some moment methods with such an operator. And the reason why a moment method will work is this. It's because we have this J not equal I star. So somehow when I take some high powers here, this thing, it looks like some lock, some clicking system somehow, which forbid me to come back. And suddenly the commutatorics become much easier actually for this. So when I say much easier, I mean there's still lots of things to be done, which as I'm going to explain in the last 5 minutes or so. But at least for the first time, it makes the moment method tractable, doable in in this context. So that's all what I said here. And yes, one quick comment is that actually long ago, well, almost 20 years ago now, Gilles Pizier asked me whether it was possible somehow to copy the techniques of Soshnikov, the moment methods to obtain norm estimates on let's say matrices like sum of U1 plus U2 plus U3 or whatever the norm of these things. And well, so I tried 20 years ago when I was a PhD. I couldn't do it, and now actually it turns out that our theorem implies that we can do it, and actually in a completely general setup. But it was not possible to do it before, and the reason was that we were missing these operator values, non-backtracking theory. So then, how do we compute this kind of objects, which are what we have to do now? Well, we have to compute expectations now, and for this, so since we have unitary random matrices, we have to use something which is called the Weingarten calculus, on which I spent lots of time in an earlier part of my career somehow. So here I'm just going to modify it a bit, the expression. In general, this X bracket which I write here in free probability, like the notation which was I think introduced by Voiculescu, would be some X with a bubble above. But what I want to do is I want to take many products. So this is the centering of a random variable, and I want to study the expectation of products of centerings of products of entries of random matrices. And why do I have centerings here? Well, because remember I said I have to remove fixed points, and removing fixed points, as it turns out, boils down to taking centerings. You just take just remove the constant part, basically. That's really what it boils down to. So we have to do these calculations. So in principle, it's just, if we just expand, this should just go straight. It's like you would just have 2 to the power t things, but we have to do it in a way that yields some actual evaluation. And for this, we had to expand on the Weingarten formula, which is a formula which tells how to compute the joint moments of entries of a random of a unitary matrix with respect to the Haar measure. So we have this formula which involves you have to look at all the possible pairings of the row indices, so which I call sigma, all the pairings of the column indices, which I call tau. And then whenever you have a pairing, whenever you have a match, then you have a function which involves sigma and tau. And it turns out that the original function does not have anything to do with this product of centering here. So when we have a product of centering, we have in addition as a data a partition, which these centerings give me a partition. And what I proved very long ago with the partitions without the centering is that you have some estimates for the Weingarten function, and it turns out that we can improve on this estimate. So somehow, when we do centerings, what we want is to avoid some pairings which leave one centering lonesome somehow. So this is somehow a friendly theorem in a sense. As soon as I have lonesome blocks, I have a penalty for the decay of my Weingarten function, which actually is which is the factor which explains a strong asymptotic freeness. So my time is over basically. So maybe I will just skip that part here. So lots of things are known about the unit. So what we have to do is we have to understand the uniformly how how the Van Houten function works as as t, if t grows to infinity along with n. So some things had been done from some point of view long ago by Olshansky, Jiang, and so on. From the point of view of moments, I had done things with Matsumoto like 4 or 5 years ago, which I was hoping to use, and which we finally managed to use with Bordenave. It was not quite enough, though, because we had not done the centering part, so we had to do the centering part. And it turns out that things still work. And then we need one last technical thing, which I don't know if I should do it or not. I mean, I would just flash it quickly. So the thing is that it is known that if you take a random like a hard distributed random matrix, if you look at its entry, and if you scale it by square roots of the dimension, then it behaves like a complex Gaussian. And what we want to do is we want to say, and actually, if I take 2, then they are asymptotically independent. So what we want to do is we want to quantify this very precisely as n goes to infinity, and we want to have more and more moments. So what we do is we compare this here with just independent Gaussians. So here you see it's really difficult to compute the moments. We have a problem, but it's difficult. And here, it's simple. I mean, this is just Gaussians. And what we have is that actually we have a surprising, maybe surprising from the point of view of probability, an inequality. And basically, the unitary case and just the Gaussian case have almost the same behaviors, that there is a strict inequality, there is inequality between both. The only price that one has to pay is that one has to accept to, not to have center Gaussian, but to slightly move away the center of mass, but to an amount which is negligible for the purpose of what we want to do. It's really like moving all the eigenvalues by 1 over some power of n, so that doesn't change anything for us. Yet we are left with evaluating this kind of quantities here, which are, thanks to the Van Houten calculation, which are actually doable eventually. And sorry for being late. I stop here.
Well, no questions from the audience at the moment, but I'd like to ask something about the theorem, just about frame numbers 13 and 14. And there was a mention of a non-backtracking matrix, and there were certain B lambdas. Is there any sort of simple interpretation of what motivates this choice of formula?
So you mean for this one here, right?
Yes.
Yeah. Well, actually, probably I suppose the answer depends from the point of view. But historically, I think that the non-backtracking operator was introduced, for people who wanted to what is with the Ihara zeta function and this kind of thing. And when people really wanted to study some things about graph theory, and later on it was also used by Bordenave and Friedman to prove that the random graphs are almost surely, like random regular graphs are almost surely close to, in large dimension, close to expander. And so what they had is they were able to handle the case where all the coefficients were 1 somehow, and then they already had some parameters like this which were appearing naturally. So we had to make some guesswork, like maybe maybe all these things should be 1 or something like this in this case. So we had to make some guesswork to see what happens when we replace all the ones here by generic operators, and looking at the proof, this kind of things showed up. Basically, that's one thing somehow. So it's really like the way this theorem was set up was some kind of reverse engineering, but in hindsight, we also have very similar functions which appear in there are these formulas by Franz Lehner, who actually give formulas for the norms of such operators. For such operators where these are free semicircles or free unitaries, and they actually involve also such formulas which are very close to that, and it's a minimizer over such kind of things. So we don't use this, but somehow in hindsight, this gives a clue that maybe this is kind of well fits to the context of asymptotic freeness somehow.
Right, thank you. There's now a question from the audience. It's basically, do we know about strong convergence for random matrix models with a potential free Gibbs laws? I suppose this relates to sort of generalized unitary ensembles and such.
Yeah, that's a very good question. I think it's not known actually. I mean, I think this is one of the to-do lists. I think in the unitary case, I think we have kind of no clue somehow. Maybe with self-adjoint, some people might have thought about it. I'm not sure, but I'm not sure there are some. I'm sure there are some actual results out here, but that's definitely a very natural question. Yeah.
Right, thank you. I'd like to thank our speaker for staying up to give this very illuminating talk on how random matrix theory discusses very specific models. Oh, we do have one more question, but I'll continue with my thanks. I'd like to thank our speaker for giving us a talk about the application of strong asymptotic freeness to questions relating to operator algebras. Now, the question is specifically about multi-matrix models. I think this will be relating to strong convergence for random matrix models, particularly multi-matrix models.
So
the question is, do we have results for strong convergence for multi-matrix models?
Yeah. Okay. Yeah. So exactly. So for single matrix model. Okay, I see. So yeah, maybe it was a clarification, right? So indeed, for single matrix model, I see that. I think there are some results. If you just take potential with one matrix, I feel this is. There are results, I think. But for multi-matrix models, as far as I can tell, I think that they are not available at this point. I don't think they are available. Yeah, I mean, so yes, the results. So yeah, I think yeah, I don't think there are results. Yeah, but I might be wrong. But
okay, right. Thank you.